It's like 1 minute after, so let's get started. I'm Steve Hastings, and this is Python Decorators Inception. And I came up with that title because when you have decorators wrapping functions, sometimes you can get functions in functions. You can kind of get, it's like the dream within a dream of Inception. And I'm going to try to make you guys completely understand decorators and break it down for you and hopefully show you a way to structure the decorators that's a little less mind-melting. I wanted to start with telling you I've put extra stuff in the speaker's notes. I don't need the speaker's notes. It's for you. So if you download the slide deck in OpenOffice Impress format, you can look at the speaker's notes later. So let's start. I want to give you just a taste of decorator magic at the beginning. This is a very naive recursive implementation of the Fibonacci function. And it has terrible performance characteristics. If we ask for the 100th Fibonacci number and call this function, it will take a long time. You might intuitively think that it's roughly 2 to the power of n because we're going to make 2 function calls at each level. And it's going to fan out. Actually, according to Stack Overflow, it's about 1.6 to the n because kind of the leaf calls are really cheap. If n less than equal 1 is cheap. So they say 1.6 to the n. Based on that, I computed that on my laptop, Fibonacci of 100, this function of 100, would take 1,000,000 billion years. And the sun is scheduled to go out in about 5 billion years, so there's kind of a problem there. But we can make one change. We can add one line that I put in blue, and I timed this as 25 milliseconds, getting to the answer. What is this dark sorcery? How does this work? I'm not going to tell you yet, but I want you to pay attention while I do some review. After the review, I will cover this. I'll come back to this example. Very basic review. What do our programs do? Well, they run. They do stuff. But I'm going to tell you they do these 4 things. You're going to create new data structures, create new code, sort of, modify existing code or data, or interact with the world. Now, that last one's really the big one. Like, all the other stuff is a prelude towards printing a number on the screen, making a graph for you, sending an email, whatever. But these, I'm going to claim, are the basic things you can do in a program. So what happens at the interactive prompt in Python? You type something in, what happens? Python immediately compiles it to bytecodes, then it runs the bytecodes, and then it's done. There's no special compile phase like there is with C and other static languages. It compiles instantly, runs the code instantly. Basically, it's always runtime in Python. And you can do any of the things on the previous page. You can print things, interact with the world, make code, make data structures. So now, here's a quick example of the 4 things. We'll make a list data structure. We'll make a function object. You're going to see a lot of this add5 function. It just, you take any x and it returns x plus 5. We can modify a data structure, append something to the list. We can interact with the world, which is a grand way of saying we can print something here. So, I think we're all on the same page. What happens at the prompt? What happens when you import? Same thing. All these things can happen. You can set up data structures, set up code objects. You can even interact with the world. You could put print statements in an import file if you wanted. And here's just the same 4 examples, and now we're imagining this is in a file we're going to import. So the whole point of this is that at import time, you're just running code. Whatever's in the file you're importing, you're going to run it. And when you're building functions, you're building functions at runtime. The def statement builds a function for you at runtime. Another point I want to remind you is that in Python, everything is an object, and that means functions are objects, which is kind of cool. You can pass them around. You can call a function and say, here's a function. You can save a function as a variable. You can modify a function. You can make a new one at runtime. I've been trying to make this point. Everything's at runtime. The def statement's at runtime, so you can make a new function. one of the things you can do is introspect a function. We can look at it. So here is a slightly better creation of add5 where we've added a doc string. But it's not a very good doc string, but I just needed an example here. So when we do def builds a function object for us, and one of the things it does is it sets up this underscore underscore name underscore underscore member variable. And since it's hard to say underscore underscore so much, we're just going to call this dunder name. So dunder name gets set up to add5 by def. And dunder doc gets set up to the doc string that we provided. And here you can see we're printing them, we're introspecting them. You know, you can look at the value at runtime, and we could also change these values at runtime. In this example here, I'm overriding the bad doc string from the previous slide with a better doc string. And when we run help, help prints the new improved doc string. So you can see we have in fact changed the function object. You can also just treat a function object like a place you can stick member variables. I'm not going to do much with this in this talk, but I'm just showing you that you can do that. So a function is a thing that you can modify. You can look at it, you can modify it, and you can make it runtime. So when you give the name of a function in Python, what you're really doing is looking up a reference to it. If you then stick parentheses on the end of it, that's how you call the reference. There are some languages like Ruby where you can call a function without parentheses, not in Python. So here we're going to make our add5 function, and then we say alias equals add5. So when we say alias equals add5, we're binding the name alias to now point to the same reference as add5. So there's one function object that now has two names. It has the name add5 and it has the name alias. And if you run alias with the parens after it, you're calling the same function object, so it's going to add 5 to the 10, you get the 15. If you print the dunder name, it still says add5 because there's still only one function object, and when def made it for us, def stored the name add5 there for us. So finally, I'm done with the review. Let's start talking about decorators. Here's an example of decorator syntax. We have an at and then the name of the decorator, and we put this before the call to def. What this does, just by looking at it, we can't really guess what it does because it could be doing anything. The 4 things that I said we could be doing, it could be doing any or all of those. It could be making new data structures, making new code, modifying data, modifying code, or interacting with the world. It could be printing something on the screen. The basic idea is that the decorator is going to be a function that is going to be called when the def statement is evaluated. So like if this is in a module at import time, and whatever's in that decorator runs, and the decorator takes one argument, which is a function reference. And what it does is exactly the same as this last line, add5 equals my decorator of add5. So the at syntax is simply a little bit of syntactic sugar, just a convenience, so that we can just write that simply and not have to write the second one. One of the bad things about this is that you have to kind of repeat yourself. You have to have add5 over here and add5 on the left over here. And if you were editing your code and changed just one and didn't change the other, there'd be a bug. So by having it all on one line and convenient, it's not only convenient, looks better, but more bug-proof. So here's our first decorator, the simplest possible decorator. Do nothing. Do nothing, simply you pass it a function reference and it hands it back to you unchanged. This is a perfectly legal decorator. At do nothing does nothing to the function. Add5 equals do nothing of add5, does nothing, binds the name add5 to the add5 function. No big change, but it's the simplest legal decorator. Finally, this is a decorator example that's actually maybe starting to be useful. Now this is an example of a decorator that's keeping track of stuff. So this is going to be modifying data. It's not actually going to modify the functions. You'll notice both of these decorators, the last thing they do is just return the function pointer back unchanged. But while they've got it, they're going to save a record of it somewhere. So I'm imagining we're writing like an API, and we have 2 types of functions. We want to keep track of the functions we've added to the API which are type A, and the functions we've added which are type B. So we make the type A decorator, which keeps track of all of our type A API functions, and the type B decorator keeps track, and all I do is just append them to a global list. So an example of how we would use this is on this slide. So our foo function is a type A function. Our bar and baz functions are type B. And after we import this file, we could then run some code to print lists of these functions. And I think that's pretty straightforward. Just loop over the lists and print them. And there's the output. So this is a way that you can make decorators to kind of keep track of functions. And this is used by some unit test frameworks. You put a special decorator on the functions you want the unit test framework to run for you, so it knows which ones to run. There's other frameworks like PyTest. PyTest just introspects everything, so you don't have to do that. But some of the frameworks require you to decorate your functions you want tested. Another major use case of this kind of decorator would be web frameworks like Django and Flask. They will have you decorate the functions that you want the framework to call when people visit your website. I'm not going to show them yet because that kind of example generally wants to have arguments. And right now I'm just showing you the simple decorators that don't have arguments yet. But I'll return to this example later. And one point I'm just going to make quickly in passing is it doesn't actually have to be a function that's a decorator. Any callable works. So you could have a class instance, and as long as that class instance has the dunder call method, so it knows what to do when it's called, you could use it as a decorator. And obviously the dunder call method is going to have to expect a single function as its argument so that it'll work as a decorator. But none of my examples are going to show this. I just wanted to note that in passing and move on. So now, the other major use case for decorators is wrapping functions. You can wrap a function by defining a new function that involves the old function. So everything's dynamic. Def is code that runs, which means you can have a function defined from inside another function. A function defining another function, Inception level 1. So here's an example of a function that defines another function. It's a nice simple example to warm you up to it. So we're calling it add5factory. Whenever you call the add5factory function, it's going to build a function object for you and hand a reference to that function object back. And this is a boring factory because it only makes add5. So it's not a very useful factory. This example, I would never do this in real code. I would just put the add5 in the source code file. There's no reason to make a factory for it. But it's legal, you can do it, and it's simple. Let's make this a little more useful. Here's an adder factory that can make any kind of an adder, not just add5. It can make add7 or whatever you want. You pass in what you want added as y. Then it makes a new function that always adds that y value and returns a reference back to you for that function. So here we make add5 by calling the adder factory and passing in a 5. We call add7 by calling adder factory and calling 7, and I just have an example to show that the add7 works. Now, if you think about it, this must mean that the y that you passed in is being saved somewhere. When it's saved somewhere, we say that the function that we make closes over that value, and we call the result of that a closure. There's multiple languages that have closures. Lisp is famous for having them. JavaScript, you have to use them a lot in JavaScript. Python, some people think that the Python closures are not as good as the other languages. They have kind of a quirk. The quirk is that once you've bound the name, you can't rebind it later. They're just as powerful as any other closures because you can work around the quirk without any trouble. I'm going to show you an example. This does not work because of this quirk in Python. Counter factory is going to make a function for us called counter, and every time we call it, it'll return a number 1 higher. So it's counting how many times it's been called. A fairly useless thing, but a nice simple example. This is not going to work because this is trying to rebind the name count, and you'll just get an error when you try to compile this code. But instead of trying to rebind the name count, we can pass in a mutable object and mutate that and have the count changing. So this is the way I would recommend to do that. We'll make a trivial class called box. Class box, pass. That's it, trivial class. So when we call the box class, we get an instance of it, and we can then stick member variables onto it. So we can say box.count equals whatever, and we can rebind that all day. That's all it's doing is mutating the class instance. So the name box is bound forever to this one instance inside the counter function. We can't rebind the name box, but we don't have to. We can rebind box.count all day. So this is the working way to make that example. So you guys are now experts in closures in Python. You know what's going on and how it works. So just one more bit of review. You probably know this, but Python has this cool, nifty feature where you can have any number of arguments of positional or any number of arguments of keywords. So for positional, you use 1 asterisk, or I'll say 1 star, and for the keyword arguments, you use 2. And the traditional names, you don't have to use these names. The traditional would be to say star args and star kwargs, KW args, keyword args, kwargs. So the example function there will collect all the arguments, and then we just print them. And we collect all the keyword arguments, and then just print those. So I have an example of calling it, and you can see we pass in 1, 2, and 3 positional. It collects those and prints those. We pass in foo equals 6, bar equals 7. That gets collected as a dictionary, so when we print that, it prints in dictionary format. The other side of this coin, not only can we collect them, but we can stuff them into another function call later. So we can collect them, and then if we were saving a function reference, we could call that function reference with the arguments we want by building up a list or a dictionary and passing them in with star or star star. So in this example, we're inserting them. Instead of calling with 1, 2, and 3, we build a list of 3, 6, 9 and star my list to pass that in. And similarly, build a dict and pass that in with star star. And you can see from the printouts that this worked. So the reason I wanted to show you this is because this is used when we write wrapper decorators. We can wrap a function by making a new function that closes over the old function. And then it can do some stuff before calling the old function, call the function, do some stuff after the old function. So you can add a whole layer of behaviors wrapped around the other function. And you can write one decorator that can work with any function, and it doesn't matter how many arguments. Could be no arguments, could be 20 arguments. It'll collect them all and paste them in and call it, and it works. So I'll show you that in a minute, but first I just wanted to show as a simple example. This isn't a decorator yet. This is just a helper function, and we're going to pass it the function we want called and then the arguments we want to be passed to it. So this is going to print the name of the function, which we find from the dunder name from the function reference, and then it calls the function, passing in all the arguments that we passed. And there from the example you can see we can call add5 and pass the argument it needs, and it works. So here we now have all the knowledge we need to write an actual decorator. So this is the print name decorator. And if you use this decorator on a function that you define, it will make a new wrapper which prints the name of the function whenever it's called, and then call the function. And it passes through all the arguments. So print name, being a decorator, takes one argument, the function to wrap. But then it makes a new wrapper for you, and the wrapper collects all the arguments and all the keyword arguments, does its thing, and then calls the saved function. So fn, you'll notice fn is not specified in print name wrapper, it's specified in the outer function. So we're going to close over fn. We're going to store that, and then we collect the arguments and shove those in there and then return the result. So def print name immediately defines this new function, and then the only other thing print name does is return this new function object that it made. And then this works as a decorator. So here's an example of using it. At print name on the add5 function, when you call add5, it prints calling add5. So that is wrapping a function with a decorator. One thing to think about, though, when we wrap the function, we made a new function object. Now, when we use def set up the dunder name for us. And if we passed a doc string in, def passes, sets up the dunder doc as well, the doc string. If you look here, I've gone back, print name wrapper is the name of the wrapper, and it has a doc string that says we're going to wrap a function to print its name. After we used this decorator, we made a new function object that wrapped add5, and now the dunder name and dunder doc are no longer correct. When we look at them, the dunder name is print name wrapper, and the dunder doc is the doc string of that wrapper function. Well, that's not elegant. That's not pretty. Let's fix this. The brain dead way to fix it is right here. We can just smash in the values that we wanted. But you know it's Python. You know it's going to be more elegant than this. Python, the functools module, provides a function called wraps. Wraps is called the decorator. It's a decorator that you apply to your decorators. A decorator to decorate a decorator. Inception level 2. So here's how you use the wraps decorator. You just add this one line that I put in blue in the middle of everything else. Nothing else has changed. So this decorator decorates our wrapper, and it's going to overwrite the dunder name attribute with the correct dunder name from the function that we passed in, and it'll overwrite the dunder doc from the doc string from the function. And I believe it also, like if there's member variables assigned, it copies those. Basically, anything that's modifiable about the function gets copied out to the new function object. So that the new function object now is a good doppelganger that looks and feels just like the old one, but it has the extra behaviors that you wanted. So now let's consider decorators with arguments. This is getting deeper into the Inception now. When we call @myDecorator with 1, 2, 3 here, it's a decorator. Well, we know that decorators are functions that take a single argument of the function reference. And in fact, we know that we can rewrite it in this form. So what this clearly implies is that when you call myDecorator with 1, 2, 3, it must be giving you back a function object, and the function object it's giving you back must take one argument of a function reference. And then you can put parens on this function reference and pass in a function and call it, and then it will do the decorator thing you wanted done. So decorators with arguments are, in fact, functions that create a function that wraps a function. Inception level 3. And that's as deep as we're going. We're level 3. It's deep enough to fully understand decorators. So here's an example, which I think is a pretty reasonable example. We're going to make a decorator that calls a logger whenever we call this function. So every time this function gets called, this logger reference that we passed in, myLogger, is going to get called, and it's going to get called at level debug. So you can, again, just to mentally break it down, when we call logonCall and pass in these arguments, we're going to get back a reference to a wrapping function. And the wrapping function then can be called, and it gets its one reference to the function being wrapped and does the decorator thing. So the top just does it in one step, @logonCall. Here we show we can do it in 2 steps. We can get the wrapping function reference and then use that as a decorator. So again, sometimes when you're thinking about at least for me, sometimes when I'm thinking about the ones with the arguments, it's like, keeping it all straight, I like kind of breaking things out a little bit when I'm thinking about them. So when you're writing the code, instead of doing it completely all in one go, I like to make a function called wrap2 followed by whatever. So this function is not itself a decorator, but it's a helper that we'll use in another slide to make a decorator. So the thing about this is that you pass it everything that it needs. So you pass it the function reference, and you pass it the logger and the level, and then it's going to generate the wrapper function that you need. So the wrapper function calls the logger, then calls the function and returns the result. So the wrapper function is closing over the logging level. It's closing over this message variable, which the message variable is using the dunder name from the function reference, and it's closing over fn, the function reference itself. So those things are all going to get baked into this wrapper. So now we finally have our log-on-call decorator defined. So log-on-call takes logger and level, and then it defines the actual decorator, which will then actually get called with the function reference. And so here we have a little bit of code that's easy to think about and easy to understand. You can see that it's closing over the function reference because it wasn't passed explicitly to log-on-call. And you can see that we're handing the arguments from the log-on-call get handed to wrap to log-on-call so that they can get written into the decorator. And then when we're done, we return the decorator. And then there's just a simple example of how you would use this. But to keep that last slide simple, I left off the @wraps. Best practice is always to use @wraps, so that when you wrap a function, you have the dunder name and the dunder doc and everything all copied like it should be. So here's just the same thing. The only change is we've added @wraps in the correct spot. So that, again, @wraps always decorates the decorator, and in this case, it decorates the inner wrap one. It decorates the function that gets created to do the wrap behavior. Sorry, I didn't explain that very well, but I think you followed it. Now this, when you look things up on Stack Overflow, a lot of the time people will just write this. And it's not wrong, but I claim it's a little harder to follow than what I wrote on the last few slides. We have @wraps, wrapper, and wrapped, all in a block. It's not wrong, so if you're ever working on one of these things and you're getting a little bit twisted up trying to think of how it works, I would say decompose it like I showed. Make the wrapping function and then make this simpler, and life gets a little better. Finally, I'm back to the Flask and Django example. So here we're showing Flask code. If somebody visits our website and goes to slant hello on the website, we want to serve up hello world with a little winking smiley, because why not? And so here's our function. All the function does is return the string we want served up. Then the decorator registers this as an app root with the endpoint of slant hello. And so this is, as far as I know, this is not a wrapping decorator. This is one of those decorators that keeps track and updates data structures somewhere else. So Flask is registering that slant hello wants to call this function. So this is a nice real example of a decorator with arguments. Now here's our do nothing decorator, this time with arguments. And it's pretty simple. We use *args and *kwargs to accept any arguments, and then we ignore them. We don't care about them. They're useless. The actual decorator takes its function reference and gives it back to you. Here you go, no change. So this safely does nothing with arguments. And that's kind of cool because you can do this. You can make the decorators optional. So let's say you import something at runtime. You can make it check for an environment variable or a config file or whatever you want. And depending on the result of that check, you can either use the actual decorator or use the do nothing decorator. So in this example, if we define an environment variable called debug logging, then we actually get the debug logging. Log on call gets set up to actually do the log on call decorator. If we didn't have the debug logging set, we use the do nothing decorator, and then there is no cost in our code. Our code doesn't get slower, our code doesn't get bigger. All that happens is that import time, it takes a little extra time, but that's no big deal. So this is an example of why decorators are better than just sticking log calls into all your functions, because you have the option to just completely not have them if you want. So now, I don't know how often you'll do this, but I did this recently. I wanted to apply multiple decorators, and since I was applying the same multiple decorators all the time, I wanted to make one decorator that applied all of them for me. So it's pretty easy. The print on call decorator just takes a function argument, so we can just call it. So we just use the inline format, basically. Since this one takes arguments, I call it once to get the wrapping function, and then I call the wrapping function. Although really, I could have just stuck parenthesis fn on the end of that first call, and it would have done the wrapping. Anyway, some third decorator. So it does all three, and then to use it, all you say is @log3. So what I use this for is I have a Flask web app, and every one of the routing functions wants to have a decorator that logs when it's called in the access log, that whenever there's an uncaught exception, prints a stack backtrace, or not prints, logs it in an error log. And then I wanted to call the Flask app route. And so I did something like this, and it made my life much more convenient. You remember in the movie Inception, they were all worried about falling into limbo and never finding their way back. That's not really a danger with decorators, but if you do have a bunch of wrapped functions, and if you just copied the code from Stack Overflow and all of your function wrappers are all called wrapper, then when you see the stack backtrace, it's like the innermost thing is your actual function, and then there's like a wrapper called wrapper, and another wrapper called wrapper, and another wrapper called wrapper, and that's kind of not the best. So if you give your wrapper functions good names, then it makes the stack backtraces more readable. You're like, oh, okay, there's the wrap for function call, and there's the wrap for stack backtrace, and there's the whatever, you know. So let's return to that first example, the wonderful dark magic of LRU cache. So LRU cache is going to be a wrapping decorator. So it's going to wrap another layer of behavior around the function that we give it. And what it does is it saves the arguments that you pass to your function, and it saves the result that the function computes in a cache. So if you call it again with the same argument, instead of computing the result, it just looks it up in the cache and just says, oh, here it is. And the cache is a Python dictionary, and Python dictionaries are fast. So instead of making 2 calls every time we call Fibonacci with any value, now we get a whole lot of them like that. So it goes from roughly 2 to the power of 100 function calls down to roughly 100-ish function calls to compute the 100th Fibonacci value. And that's why it takes only 25 milliseconds on my laptop, because it's only making about 100 calls instead of this incredible exponential behavior. LRU cache is one of the many fine features of Python 3.x. One of the things you get if you jump ship and go to Python 3.x. If you are stuck in Python 2.x, you can get it. There's a couple places, and I put links in the speaker notes. And finally, I wanted to end with an example. I did say that decorators can do almost anything. Somebody on Reddit made a decorator that runs the function as root. It takes the bytecodes of the function, serializes them, ships them over to a new process that it spins up, along with the function arguments, and the new function runs sudo to root. So if you have sudo set up in your system to prompt for a password, at that point it would prompt for a password, but you could also set up sudo to just do anything and trust you if you want. So you could have @sudo sprinkled throughout your code, and everything it was doing would just run as root. It's clever and it's scary, but it shows the crazy power that's possible with Python decorators. So that's all my slides, and we've got plenty of time if there's questions. Question?
Okay, so is there going to be, so if I wanted to use LRU cache along with the flask, then order's going to matter, right? So which direction should I put those in so that I'm not trying, so I'm caching what I actually care about and then delivering that as opposed to trying to deliver the cache. If that makes sense.
I see. Well, okay. LRU cache is going to be one of the wrapping decorators. Oh, let me repeat the question so that people watching the video know. He's wondering if you were trying to mix LRU cache with the flask decorator, what order you should do it in. So I would do, okay, so if it's like an onion, the inner layers are the ones closest to the def.
Okay.
So I would put the LRU cache closest to the def, and then you'd want the flask wrapper outside of that.
So it's going to be like bottom up in that case. It's not going to be top down.
Because what you want, whatever function object you end up with, you want flask to call that.
Right.
So if you call the flask thing too early, you're registering a function object that will still exist. And then you're adding wrappers on top of that with new behavior you want, but you're not passing a reference to that to flask. So flask will be calling the wrong level. It'll call straight into the heart of the onion. It won't be calling the outer onion layer.
Yeah, okay, so bottom up is what I was
Right.
going after.
So something you kind of glossed over, with decorators, you can have multiple decorators on a single function. You just have them on separate lines. So if you had @A, @B, def, foo, then this is the same as defining foo, and then foo equals A of sub foo, and foo equals B sub, or sorry, it's the reverse order. B, the lower one happens first. So if you want the LRU cache to bind more closely to the function, then you would have the routing first, and then the decorator for the LRU cache, and then the def for the function.
Yes, so somebody just pointed out that I completely failed to document an example of multiple decorators and talk about the order that they're evaluated in. So the important point is that as they get closer to the def, they get done first, and then it goes upwards away from the def. So if you have @foo on a line, then @bar, and then a line, and then @baz, and then finally the def. Baz would be done first, and then bar, and then foo, in that ordering. Question in the back.
So you showed us some stuff of doing things before and after a function in a decorator. But the @wraps, I believe it was sort of manipulating stuff in the function, like the dunder name and dunder doc. Can you show us some examples of how that's performed?
So you're wondering how the @wraps decorator is modifying the function?
Yeah.
Okay, so
Or if that ends up being complicated, some simpler example of how the function itself is modified rather than simply things happening before and after.
So you can modify things in a function by just doing it. You have a reference to the function. If we say here, add5 is our reference, and if we say add5 dot dunder doc, we can then use equals to assign that. So here's an example of just modifying that. So what happens is def builds the function object, then the decorator gets called. So the function object gets passed to wraps. And then wraps has a function object, and then wraps just so wraps is one of the ones that takes arguments, right? So its argument is you pass the function object that you're wrapping. So wraps looks at the function object to get the dunder name, the dunder doc, and anything else that it's going to copy. And it's going to have to gin up one of these little functions, like I showed for the decorators with arguments. It gins up a little one-off custom function, which then actually gets called to do the wrapping. And that function gets the newly made function passed to it. So then it has all the pieces it needs. It has the function that's being wrapped. It has the new wrapper or the new result of whatever the decorator did, which is the new wrapper function, and it can then use those two pieces to copy things from the one to the other. Does that make sense?
Yes.
Question?
Oh, for the cache, the LUR cache.
LRU. Least recently used.
LRU cache. How long does that stay after? Does it stay after it's being called, or does it just stay during the call of that function?
So the question is, when you use LRU cache, what's the lifetime of the cache?
Yes.
So the lifetime of the cache is going to be the same as the lifetime of your new function object. So when you wrap it, it makes a new function object that has the cache associated with it. Like right here on this slide, I have an example, add 5.x equals 3. So we're binding the name x as a thing in the object and storing a 3 in there. And that will float around with the function object forever until the function object is collected. And it's the same with the cache. The cache is assigned in as like a member function, a member variable somewhere. The wrapper behavior updates the cache. You can find discussions of how it works, and you can find recipes implementing it. There's very simple ones that will grow without limit, but the one in Python is called LRU because it just keeps some finite number, and it keeps the most recently used of those. So if, like, let's say the number is 100 by default, it would keep the 100 most recently used. So it's a more complicated implementation, but it doesn't have the problem of growing without limit and burning up a bunch of memory.
You can set it to 0 if you just want it concerning memory.
And somebody says that you can set it to 0 if you don't want it to limit and you want to keep burning memory. So, question? Yes?
Just a quick comment. The data binding example you gave with using the blocks and stuff,
Yes?
that's not necessary in Python 3. You can actually use the non-local keyword to specify the scoping of the variable to be to the next cell variable, and then you can skip the trick, which is totally valid and definitely the way to do it in Python 2.
So it's a comment from a Python expert that in Python 3, the trick of using the mutable in the decorator in the closure. Using a mutable in the closure is not necessary because you can use the non-local keyword, and then you can get away with rebinding the name inside the rebinding the name of the closed over data.
Only in Python 3.
But only in Python 3. Yet another reason to make the switch. Any questions? Yes.
One of your early slides was a definition of the wrapper of a wrapper, and it was basically just the math of f of n of f of x. So if you're doing math on your data, when do you decide, oh, I shouldn't just do math, I should use wrappers? You said there's a convenience in reading, there's an advantage in memory utilization. This seems like a pretty extravagant implementation for what mathematically might be really simple, or at least in a formula. So I think what I'm asking is, if you're just dealing with numbers and calculations, you do this for memory management.
Okay, so the question is, when would you want to make a new function object with an argument kind of closed over and saved, and when would you just want to just make functions that you pass all the arguments in and call them? Is that pretty?
I think so.
So that adder factory thing example wasn't really a thing that I was encouraging you to do, but I wanted to start simple and build up to decorators with arguments. The whole point of a decorator with arguments, it has to make the decorator function that takes one argument, the function reference, to be decorated. But if we want to pass arguments to it somehow, the way we do that is by closing over them and making a new function object that closes over them. So in that case, we're kind of getting around. So the contract is a decorator takes one argument. It takes the function reference. So we can get around this limitation that we can't give it any other arguments by closing over other arguments in a new function and then using that new function. And so just to sort of teach you how that all works, I made this factory thing. That factory thing is not a very useful trick in real code. I mean, it is. Okay, there will be times when you'd want to make a closure like that, but you wouldn't want to make it for something as simple as adding a number. And I'm a little fried after giving the whole talk. I can't think of any really good examples right now. Maybe after I'm done talking, you can see me or something. Any more questions?
Could you actually just go back to the first page to the slides there? Link.
So the question was, can you go back to the slide that has the link to download the slide deck? Question?
Sorry, I came in late. Did you cover the context manager decorator at all?
Nope. Nope.
You can use it to wrap to use the with something an object as a function. So like the file opening object, it was a useful one.
And you yield in the middle to switch between enter.
Yeah. It was a cool one.
Right. So the question was, did I cover the decorator that's used to conveniently make a new context manager? And no, I didn't cover that, but that would be a good one to look up and study if you want to.
It's in the context lib.
It's in context lib, and I believe it's contextlib.contextmanager. It makes it very easy to write a context manager, and context managers are cool. Any more questions? Thank you very much for coming.